thank you. I will take the opportunity of this first slide to advertise that I recently moved to Canada in UQAM. So it's just because I realized that some people don't know. And so now I'm managing an OSL lab. So today I will speak a lot about OSL dating. In active tectonic, one of our key questions is to understand the seismic cycle and also the fault activity. And when we look at the seismic cycle, we can go from the seismology or the geodesy, that is the short term, up to several million of years if you use the geology. And in between, you have the paleoseismology. And what is great with the paleoseismology is that we can look at the seismic cycle in trenches, but we can also try to determine long-term slip rates. And for that, you need the offset and dating. Thanks to the pioneer work of Paul, I think that today we are able to constrain the offsets with quite good constraint, let's say several 10 centimeters, thanks to the images and the DMs. But today I will speak about the dating, because in fact, most of the debates about the long-term slip rates is coming from some issues that people have with the surface dating. So I will speak about radioactive methods like the cosmogenic, but also with dosimetric methods like the luminescence. Speaking about the debates, I think the Alting-Tag is really the famous fault where they have many debates about the slip rates. And when I was a student, I was really impressed by the number of papers and all the discussion in the papers. And every time I'm always telling to my student, you have to read these papers. So everything started with Paul works with Landsat images. And here in blue, you have all the works done by, let's say, Paul's team. And as you can see, you recently have a paper in 2024. And in green, it's papers coming from other teams, and they have many debates about the slip rate along this fault. Oops. Going back to the dating, so the cosmogenic dating. I put in this slide in red all the papers speaking about the methodology. So you can see that since the 80s, they have many papers looking at the methodology, how to increase the use of cosmogenic dating. And in green and in blue, I also put the papers that are using this method for determining slip rates. So the first paper, the two first papers that really used cosmogenic dating looking at active faults, it's the paper from Biermann and the paper on Owens Valley, and the paper from Rizza. And it was the first time that the slip rate was determined along an active fault, along the Bok fault in Mongolia. And 3 years later, Jérôme published the first paper using cosmogenic dating along the Colon fault. And you can see that at the beginning, you have just only a few papers, and really quickly, the number of publications just increased. So it's really difficult to put on this slide all the publications. So I'm sorry if I'm forgetting somebody. And also, I would like to thank Jérôme that really helped me to do this slide. He fed me during the past 2 weeks with many papers, and it was really great, in fact, to see that everything was done between the 90s and 2000. And looking at that, in fact, when you look at the optically stimulated luminescence, it's mostly the same. Everything was really done between 90 and 2000. You really have a change. So for the luminescence dating, before the 85, in fact, it's this paper that is a real break in the luminescence dating. Before, you have the thermoluminescence dating. And thermoluminescence dating was not very great for sediments. And then everything started here, and you have now the optically stimulated luminescence that we call OSL. And it's the same, in fact. The first papers that really used OSL for paleoseismology, it was the paper more or less from Naomi Porat on trenching and also to determine a fault slip rate. And it's the same. If you look at the number of publications, it just increased. And I think if you just Google luminescence dating, it's more than 4,000 papers now. Not about like just paleoseismology, but it's in the world. It's really increasing. So if we look back over the last 3 decades, we can say that a huge amount of work has been done and going to numerical dating methods. And now quaternary researchers really went to this dating method, and we have a numerical age estimate. But the use of the dating method also shift to the production of numerical chronologies, but they are not based on any calibration processes. Also, I would like to say that we are stretching these methods to their very limits, and I think we have to welcome some criticism about that. And dating methods still require a methodological adjustment. But today, I think we mostly all agree that in a landscape, we can date everything. So now I will speak about like the limitation and the assumption that we have when we are using this dating method. So in fact, common questions from the 90 up to today, it's, okay, where is the original surface that I want to date? If I use cosmogenic dating, should I choose like the boulders, the big boulders, or the small pebbles, the gravels, the sand? And what is the previous exposure history of the sediment before to be redeposited? Do we have shielding? Like it was one of the questions. What is the erosion rates? And also, when you look at the paper and when you try to compare your data with other papers, in fact, sometimes you have minor difference because we are not using the same production rates. And also, we still have no production rates for Asia. And I'm quite amazed about that. So we have to work to finally have a production rate in Asia. So now if we, for example, I'm always using an old number. It's 4.02 atoms per year. That's, in fact, it's not really from this area. And if you look like some people really have looked at production, like at local production rates, and in fact, you can see that you really have difference. So if you look at very old deposits, it's not a big deal, but for young deposits like moraines, that could really change your age, like several 100 years sometimes. So it's very important, I think. And we have nothing. So we are using like a mean production rate, like a world mean production rate. So when you look at the source here, so what we have has a limitation. It's that we have freshly sediments that are eroded from bedrock sources with long-term exposure history, with short, if any, sedimentary history. It's meaning that if you use cosmogenic dating, you have inherited concentration. You may have some shielding by ice or snow. And looking at the OSL, we know that it is challenging because we have partial to incomplete bleaching of the quartz and the feldspar. But also, we are dealing with very unstable OSL components. It's meaning that the quartz or the feldspar are not good dosimeter. Then, when you go to the transport, we have mixture of sediments with very different residual behavior. We have short to very long sedimentary history, and we have changes in the river course. So it's meaning that we have reworking, weathering, or gradual exhumation of the sample. We also have long residence time now. So it's meaning that your ratio between different isotopes can change. Looking at the OSL, we may face some problem with the water turbidity. It's meaning, again, you have incomplete bleaching. But now we are dealing with very different luminescence characteristics. And now, if we look, for example, for the 14C, we may have some reworking of this material. Looking at the zinc, so now we have even like bigger difference with very, very large different residual behavior. And now we have long to very long sedimentary history. So it's also here where you have large aggradation and you have a very long storage of the sediments. Speaking about luminescence, it's maybe the area that it's great because you suspect to have well-bleached sediments there, but you have very different residual behavior. And sometimes you have no more feldspar. Also, we are dealing with extreme events like extreme climatic events or earthquakes will trigger drastic changes in the course of the river and in the sediment supply. It's meaning that before to really use our conventional dating techniques, we have to understand the stratigraphy. So now I will give you like some examples that I worked during like the 10 past years. And I will start with the 1934 Bihar Nepal earthquakes. Because it was also a debate. Everything started with some Sapkota thesis and the first paper published in 2013. And a year later, Laurent and collaborator also published different other results about the dating along the MFT. And as you can see, they have debate because they have another team that disagree with the results. And and they have two other papers, one from myself and one from Magali Rissner. Also, we were many students, postdoc students, working along the MFC. And I think something was missing yesterday when we were speaking about Paul that I would like to advertise here. We are all girls, all women. And I think really Paul pushed women to science. And coming from his generation, I think it was quite exceptional. And yeah. So here it's the Circola site where everything started for the debate. So you have here the result from some Sapkota and Laurent Bollinger. And on the right side, you have the paper from Wisniewski. They disagree about the interpretation of the log, but it was not exactly the same exposure. But in fact, when you look at the papers, the big debate is about the dating, the 14C dating. And now I will go, and I put some great picture from the field because we really spend a lot of time in the fields along the MFT. And so you can see some of our activities along the MFT where we did like LiDAR. We also did some geophysics and we really spent time looking for charcoals. And Paul was really pushing us. And sometimes some of the people were really exhausted, but so I will speak about the Charnat-Kola Trench. So the Circola is here, and the Charnat-Kola Trench is a few 10 kilometers on the east. It's a huge trench, And as you can see, one of the wall collapsed. But in this trench, so this is the paleoseismological log. And what we can see is we have like rupture, and we also have huge colluvial wedges. In this trench, they have like 230 samples that were collected, and we dated 69 of them. And first of all, we have really rare modern ages. And if you look carefully, it's in blue, and it's always in the top of the trench. Now, if you look at the dating, most of the ages, they are around this age before to be calibrated. And when you try to calibrate them, you're always in a period where we have a flat calibration curve. It's meaning that you have a lot of probability, like different probability for the age. What we have done a first model where we put like the 69 sample in an OGSCAL model, and we run the sample telling, okay, we think we have 3 event horizons, 1, 2, and 3. And what is the age of the earthquakes? And OGSCAL will give you these results. And as you can see, one of like the best event horizon for a surface structure is this one, because you have fault termination just there. We were suspecting that it was the 1934 earthquake, but it doesn't work. And as you can see, all the post-event sample and pre-event sample return the same ages. And you have a gap of more than 140 years between 1934 and the peak in the probability. So, in fact, we suspected that most of our detrital charcoal were just reworked. So we did like a very simple model to try to minimize some inbuilt age, transport, or reworking processes. And what you see, it's again the event E2 that we suspect to be 1934. We are close, but we are not still at 1934. And also, the colluvial wedges may in fact not correspond to seismic event, but more to free-phase scar degradation by weathering events. The last model is, in fact, we input the 1934 earthquake in OGSCAL. And in fact, all the sequence is giving a very low probability, but it agrees with this event. So one of the main things on this range is that after the 1934 earthquake, we may have very large aggradation, like up to 4 to 5 meters of sediments on top of the event horizons, and that most of the charcoals were just reworked. So it's meaning that, in fact, we have artificially aging in the deposition of the sediments. Looking at the cuticola, that is a few 10 kilometers again in the east, we are dealing with the same problem. And also you can go and see Laurent poster this afternoon or during the lunch. But in fact, it's not a big surprise because, in fact, when you have radiocarbon ages, in fact, we are not determining the age of the deposition. Because before to be deposited, you have to have your wood, a fire, so initial deposition. The charcoal is in the river, you have some transportation, and then finally you have the deposition. It's meaning that when you are trying to date a unit, in fact, you are always an older age. So it's meaning that statically, in all the trenches, we have old ages. So we are overestimating the age of the deposition. And for this reason, I think we can say, okay, so let's have a new look on all the trenches along the MFT. Also, I just would like to say that if you really want to have a good constraint on your age, you can use the dendrochronology because you really have a calendar year, but I think we can only use it on 2 to 5% of the case. It's just to highlight very recent works that were done with a portable OSL along colluvial wedges. And in fact, we know that with the luminescence in colluvial wedges, we are dealing with the same kind of problem with the radiocarbon dating. And what is really interesting with the POSL, it's Gray and Duros, they show that in fact, the event horizons, speaking about dating, it's not localized where we put the event horizon on your log. So it's very important when you collect your samples. Now I'm moving to the Tian Shan, and I put Paul map. I will not put my map because I think, in fact, it's mostly, he already mapped everything. So I will speak about like the Talas-Fergana fault. It's this huge strike-slip fault here. And when I started to work along the Talas-Fergana fault, they have a big debate on the slip rate. So some paper were offering 11 to 16 millimeter per year for the slip rate when the GPS show you 2 millimeter per year. So it's a big difference. And I went along the Talas-Fergana fault and I found a good site. And here I decided to put to use a cosmogenic profile, but also use radiocarbon dating and OSL. So I put all the possible dating. I know that some people will say, don't do that. It's too dangerous. but I did it. And I also made a new strategy for the sampling and for the chemical preparation. I used the same pebble, and on the same pebble, I did the chlorine, but also the regular protocol for beryllium and aluminium. It's meaning from the same pebble, or it was amalgamated pebble there, I have finally 3 isotopes on the same sample. It's meaning that, in fact, I cannot invoke any like difference in inherited history, because if you're using one sample for chlorine and one sample for beryllium, okay, yeah, maybe they have different history, but this is not the case. And first of all, in the profile, I don't have one single exponential decrease. I have, in fact, 3 exponential decrease. So I have to model the profile doing 3 different steps. And doing that, we have very good agreement between beryllium and aluminium, and also with the chlorine for the first 2 units of the profile. And I have some difference at the bottom, but it's because here my samples, the natural chlorine concentration was really high. So I cannot really, I'm not really sure about the production for the 36 chlorine. And the ERSL age is going very well with the profile as well as the 14C dating. It's meaning that the Talas fault is slipping more about 2 to 6 millimeter per year. This is at the termination of the Talas-Fergana fault. I think it's one of like the best place I went. And here you have fluvial terraces that are offset and uplifted by a thrust fault. And I did the same, but this time I used single pebble and I did my 3 isotopes all together. And as you can see, it's working really well. And I have an age of around 32, but I still have some troubles when I'm using the chlorine. And it's everywhere like that when I'm using these techniques. So now I'm moving to Taiwan. And in Taiwan, we went along the Pakwa tableland where Martin, Marilyn, Lionel Siam also worked. And here it's a small compilation of all the ages. You will say, ooh, this is really bad. You don't agree. I will say, in fact, I think everybody worked very well. And in fact, they may agree for some reason. But we decided to work on this small level here. On the other sides of the different terraces, where we already have a radiocarbon ages of 31 Ka. So what we have done here, we have done a profile, and I collected many samples for cosmogenic and many samples for the OSL dating. And this is the result that I have. So for the OSL ages, first of all, they are stratigraphically consistent. That is good. I was quite happy with that. Going from 74 to 10,000 years. And I also use the advantage that when I'm doing luminescence dating, in fact, I have many, many data in the background. So I look at the signal and I look at the OSL sensitivity. The OSL sensitivity is the natural luminescence of your grain. And what is interesting is that we see that the OSL sensitivity is growing. And this, like 37 counts per gray and 57 counts per gray, it's in fact what you have, bedrock, like luminescent sensitivity when you're looking at bedrock, are grains that have no sedimentary history. I also used the ICP-MS measurement that I did to have my dose rate. And what is really interesting, I have 49 elements. Looking at the elements, I use three different elements that people are using for sediment tracing. And what I can see, in fact, I have a big shift in my elements at this level, when I'm starting to have an increase, in fact, a real increase in my OSL sensitivity. So the question is, do we have change in the sediment provenance right there? So now looking at the cosmogenic dating, we have two different exponential decrease. So again, I cannot just model one single profile, and I did it with 3 steps. And I put my OSL age on the top because I have 1 meter of a unit that is shielding my profile. Doing that, this is the age that I've got for the cosmogenic profile. So it's very in agreement with the OSL. And I have something that I can only calculate an erosion rate for the second unit because it's at steady state. So now what is interesting, it's in fact, going from this section, I can see in fact many different units and some changes in the sediment provenance. And something is changing here, right there. At this age, if I look at the OSL dating, and it's going very well with what Martin proposed in 2007 about the fact that the starting of the growing of this fold was around 55,000 years. So I think combining all the dating methods, it's very powerful because we have something more about what is going with the sediments. What is the history of the sediments in the river? So now the big question about this site is, okay, this change that I'm suspecting, is it related to tectonics or big river drainage capture? And this summer, we will test some new luminescence on zircons, but we will also do uranium UPB dating to look at the provenance of these sediments. Speaking about luminescence, I think the luminescence has a lot of new perspective. I spoke about the OSL sensitivity, and the OSL sensitivity now is a very hot topic debate in luminescence because, in fact, they can be used as sediment tracer, and this is very powerful. And the OSL sensitivity is, we know, so the key idea is that the sensitivity is coming from the bedrock origin, but also is depending of the erosion transfer deposition cycles that the grain have recorded. The partial bleaching, it's always a problem when you want to do OSL dating. But in fact, many people now are using partial bleaching to in fact understand and try to reconstruct some history of the grain transport. So it's meaning, in fact, what is a problem can be used as an advantage with the luminescence dating. And to finish, I just want to show something that I did about the partial bleaching and the POSL. So the POSL is this small tool. It's a portable OSL reader. And so what I've done droning because I'm from Paul's team, so I was trained to high resolution DEM. I use a regular, like a normal reader, a regular one, and the PUSL. And it was during the COVID situation, so we cannot go out. I have to find something very close to my lab. And I went along the Sèvres River, that is this river, and we just went here on this on the riverbed. And what we have done, we have collected the first centimeters of the sand at the surface, first centimeters. And we are pretty sure that it will be bleached because we came 15 days after a small increase in the level of the water. And we were really surprised because this is 1 meter by 1 meter, 1 meter by 1 meter. And what you can see, it's in 1 meter, you have a lot of different residual doses measured with the PUSL. And some of them, they are really high. It's meaning this is not bleached at all. And sometimes this is very bleached. And so you can see that on a scale of 1 meter, but you can also see some like many like distribution on this area. It's meaning that in fact we have high variability of the bleaching. Why? So what we have done is, in fact, so I just show you like the data from this part, and now I will show you something that happens. So in 2020, they have this big climatic, let's say, input in France, in southern France, that created the big flood in Saint-Martin-de-Vésubie, so it's the Alex storm. And a few days later, the Sèvres, the same river, has a huge flooding. And this is the record, like the record of the river. And as you can see, it's a very big input of water in the riverbed. And we came, in fact, we collected the samples 47 days later. And I did the same. What I've done, it's, so first of all, here you have like the differential DM from the two study days, let's say, where in fact you have a difference up to 4 meters. You have sometimes 2 meters of aggradation, and sometimes you have even 2 meters of erosion in the channel. We also have have done some PUSL measurements, and as you can see, this time I increased the number because it's working very well. You have 5 minutes of measurements. You can do that in the field. This is great. And what we see is we have a big like difference again in the residual doses. But what is interesting, it's what I showed you just before. The maximum value was there. No, look at that. I'm on a very higher dose. It's meaning that after this storm, a lot of sediments came and they are not bleached even 47 days later. So it's something that we have to understand if we want to resolve the partial bleaching with the luminescence dating. So I think they have a lot of great potential with the PUSL because I use the same sediments and I measured them on a regular reader. And what you see, it's what comes from the PUSL, what comes from the regular luminescence reader. They mostly agree. It's meaning that we can maybe calibrate the age. And it is to finish. It's just to say that I think that using a dating method is sometimes still limited by a lot of assumption and limitation that we have. And the age of the deposition, it contains, in fact, many things and inherited history that is included in the numerical dating. And I think it's never really discussed in the paper, and it should be discussed in the paper. And also, I think that combining all dating methods is great. That luminescence is really powerful. Stay tuned. Many things are coming in that. And also, looking at what we can do with the PUSL, what we can do with the sediment tracing, I think we may have some future convergence between the dating method, the sediment transport, and the earthquake geology. Thank you.